to start the next lecture. I told you during the previous lecture that this previous one was the most important, because during the previous lecture you learned that if you assume that an accretion disk is Keplerian, it is stationary, geometrically thin, optically thick, then all you need to know is just the accretion rate, the black hole mass, and then everything is specified as a function of radius. In full GR, you need to know the black hole spin additionally, otherwise you don't. And then you can calculate the flux, which is dissipated as a function of radius. You can have the effective temperature, you can actually calculate the spectrum of the disk, so you know just everything, right? So today's lecture looks like it's completely useless, but it is later important when you think about limitations of this stationary approach. So there will be a lot of equations and mathematics, and they will be important when we will talk more, particularly about time dependence, but that will have also consequences about the vertical structure, this corona formation, all those problems which are not, they cannot be addressed if you use just the standard picture. So we have to go beyond the simplest description. But still, it will be the standard Shakura-Sunyaev picture, and at the end I will show you the original equations of Shakura and Sunyaev, and I will summarize how they work. So what we now want to learn is something like this geometrical thickness. We want to calculate it, then we can check whether our assumptions are correct. We want to know the disk local density. We want to know vertical structure, because this is later important when you irradiate, for example, the disk from outside, etc. So previously, I showed you that you don't need any information about the viscosity. But finally, a miracle cannot happen. If we want to know the disk vertical structure, the disk thickness, and everything else, equatorial plane parameters, then we need this viscosity. And here, this assumption of viscosity comes. So what we here assume after Shakura and Shakura-Sunyaev is the following new idea, their new idea at that time for the viscosity. The Viscous torque, which was mentioned during the previous lecture, but then we got rid of those, of this quantity, just combining two equations, right? Now we need that, and we say that the Viscous torque is proportional to the total pressure. Oh, let's say in general pressure. We will later discuss other options than the total pressure, but in standard picture, we have here the total pressure, which means the gas and the radiation pressure inside the disk, optically thick disk. So what was the motivation for this assumption? It's not quite obvious, but first, dimensionally, it's okay. You can check that viscous torque. If you look at those equations, for example, you can trace the dimension of this quantity. It has the dimension of the pressure. Second, already Shakura and Sunyaev, in their paper, they talked a lot about magnetic field. Their intuition was that this viscosity is probably magnetic in nature. Later, it was really shown that magnetorotational instability is responsible for viscosity in accretion disks. And if you have a magnetic field, then it can be in equilibrium with the matter. It can be of lower amount, but it would, okay, sorry for that, but it would be sort of proportional to the pressure, because pressure and B square divided by 8 pi are kind of energy and magnetic energy density. Yes?
Is a Navier-Stokes form of the viscous stress assumed also? Proportionality with the gradient of the velocity field or not?
Yes, it's all done later properly, and I will show also these equations. But specifically, we do assumption as before, that only r phi coordinate is important. Phi is this rotational angle, and this is the form. So if the viscosity is actually turbulent, not magnetic, and some people argued for some time that it's turbulent, it also can be expressed by the motion of the turbulence, like size of the turbulence cell and velocity of the turbulent cells, etc. And then in front there will be a coefficient alpha, which tells you that this convection is, well, smaller than the disk thickness, slower than sound speed, etc. And so it's convenient to have certain coefficients, but the scaling with total pressure would be still okay. So after them, we will assume this form of scaling of the viscous torque. So now even this viscosity is studied experimentally, because the whole setup is like that, right? You have a Keplerian disk, you have differential rotation, because the angular momentum depends, the angular velocity depends on the radius. So in the laboratory, people study this kind of behavior. For example, here, this is the picture from the laboratory, where they use two cylinders rotating with different angular velocity. They put the material there, and they see what is happening. So such a flow is highly unsteady. You see that some kind of turbulence develops, whatever. If you use magnetorotational instability, we will talk more about it. In the linear approximation, you see that this instability grows. But what we finally assume, that a kind of steady state forms where this boiling leads to the transfer of the angular momentum from the region where this angular momentum is higher to the region where this angular momentum is lower. And this, well, the matter has to lose the angular momentum, right, to flow in. So we here will assume that this kind of complex situation sort of saturates, and that's it. So for the Navier-Stokes equations, we will use them, that's true. But we will start with the equation of hydrostatic equilibrium, because that solves, that shows almost immediately part of the motivation why we are doing that and what additional information we are getting from this. Previously, we didn't use hydrostatic equation at all. So this is the Euler equation in general form, but of course we assume that the situation is stationary, so we have no time derivative. Here I copied from the book, so they used theta instead of phi. Sorry for that. That's not typical. So of course we have no dependence on the angle phi because we have axial symmetry, so that is dropped. And we assume that those viscous torque elements are not existent, so that's gone. So here we have a vertical gradient of the pressure, and here we have gravitational force. And there are those two terms. So now what we do is we say, well, velocity in z direction is not important because it should be smaller than velocity in r direction, and that is also small dynamically. So we will drop those terms in addition. That's great. Now we are left only with this equation. And here, this is the gravitational force. This is the gravitational force at a distance r from the black hole, but at the height z, right? So basically, this gravitational force is acting in this direction. But now we can decompose it into two directions, horizontal and vertical. Horizontal will be balanced by the centrifugal force, but here we need this, okay. But here we need only this component. So the total expression, correct expression is like that. Of course, we are doing Newtonian case, no, not full GR at this moment. But now we assume that z is much smaller than r. We assumed optically, geometrically thin disk, right? So we can neglect here this term and this term, and it looks then much simpler, right? This will be our hydrostatic equilibrium equation. So the vertical gradient of the pressure is equal to this. Later we will do things much less carefully, but in the case of a hydrostatic equation, it's easy actually not just to average whatever it means, but to integrate this equation in the vertical direction if we assume polytropic approximation. That's not good approximation, and in many cases, it's not really excellent, but well, it's a nice exercise. We did that in the case of spherical accretion. So if we have a polytropic approximation, we have a relation between the pressure and density. We don't need temperature, so then we have two quantities here. So we have here z, and here just one thing, density. Right? So we can integrate this equation. You can check that this is the proper integration, and then we have integration constant. But this integration constant, and here this constant, this is not quite elegant. We don't know what to do with those constants. So then we have to think about how we want to parameterize this situation. We want to get the disk thickness, total disk thickness, which I notify here as h, and at the disk surface, the density is 0. On the other hand, when we are in the equatorial plane, then the density has the value of the equatorial plane, right? And then z is equal 0. So putting those boundary conditions, we can express those constants more conveniently, and we can get rid of this constant going back to the idea of pressure. So we return with the pressure after integration. I hope you see that. because otherwise we would be here left with this K. So now we can put this K as P equatorial divided by rho equatorial to power gamma, right? So now we have an expression which is quite nice. It still has this gamma here, this polytropic index 1.4 or whatever. But let's say, well, okay, it's just a numerical factor. Let's drop that. Let's drop that. There is no such thing. So now I told you that the sound speed square is the ratio of the pressure to the density. So now this is the sound speed square. And here you have Keplerian velocity times h. So you have to replace this with the sound speed square. Now, Keplerian velocity in that case also is not intuitive. It's more important. It's more convenient to use the velocity in the phi direction. So then you express velocity, angular velocity by linear velocity. And you get an expression which is quite nice. That expression tells you that the ratio of the sound speed to the Keplerian velocity is equal to the ratio of the disk thickness to the radius. So that means that we assume that this is much smaller than 1. That means sound speed is much smaller than the Keplerian speed. That shows you that the motion in phi direction is highly supersonic, right? On the other hand, if this assumption is not satisfied, then you can have complications. But basically, you have the situation that this motion in phi direction is highly supersonic. And you can show actually that if you don't assume polytropic approximation, but if you assume something reasonable, you will get the same result. So it's just a general statement. On the other hand, if we don't care much about coefficients, it's much easier to get vertically averaged quantities. Because then the procedure is like that. Instead of density, you cannot use density at the surface because it's 0, so you use the density at the equatorial plane. You use for the derivative of the pressure, you use pressure in the equatorial plane divided by the disk thickness. And here, instead of z, you use h. And that's it. And you have vertically averaged equation of the hydrostatic equilibrium in the disk. Coefficients are not very important because they are not very accurate anyway. But it's nice to have a simple equation. So sometimes we solve this hydrostatic equilibrium carefully and we integrate. Sometimes we use just this kind of approximation. Depends on the aim. So now we will have a look at radial force equation. So again, this is Navier-Stokes equation, full. Assuming stationarity and axial symmetry, we get rid of this. Then we can neglect the term which contains the velocity in vertical direction. We have no outflow, so we always drop this term. But we have here gravitational force, attraction in the direction R, directly towards the black hole, we have centrifugal force. So they will dominate. But there are also those two terms. So normally, when we do Keplerian disk, we neglect those terms. But before we do that, the equation should be written in such form. So normally, doing Keplerian disk, we assume that omega is equal Keplerian velocity, and this is 0, right? But now, having this vertical equilibrium, hydrostatic equilibrium, we can test what are the assumptions behind this. So this time we average, sort of, not with respect to z, but with respect to radius. So we write that dp over dr is sort of p over r. And we had this expression before. So using this vertical equilibrium, we can express this term in such way that here you have, for example, this term times r times h over r square. If h over r square is small, and it is, we assume, then of course you can drop this term. The same goes for that term. It's so similar. So I stress again, this is a very important assumption behind the Keplerian disk. If you don't satisfy this equation, you shouldn't use the Keplerian disk. And we will see that it relates to the Eddington ratio. But we will see that later. So now we will have a look at energy conservation, because we need more equations to solve for the disk vertical structure. And we discussed this equation already before, but then we just integrated this equation with respect to the disk thickness to get rid of the viscosity. Now we don't integrate. If we want to solve for the disk vertical structure, we have to keep full equation, but we only replace now this TR phi component with this alpha p tot assumption, and we have a second equation. And here I remind you that pressure is the total pressure. More explicitly, this total pressure consists of the radiation pressure and gas pressure, right? This is the Boltzmann constant, this is the hydrogen mass. This term describes the ionization level of the material. So it depends on ionization stage. But you see that you have here the temperature. So here we have flux. We had one equation for the hydrostatic equilibrium, but we still miss one equation. So we need one more equation to solve for the disk vertical structure, because as it is, we have no equation for the temperature as a function of vertical height in the disk. We only have the effective temperature, but this is not what we wanted. We want now more. And this is where radiative transfer comes. This is really very, very complicated issue. So I will briefly mention some things. Some things will be skipped, and Sometimes I also have problems with pi standing in front or not standing in front. So if you have a problem of pi standing in front or not standing in front, ask Agata Różańska. She is really now expert in this pi in front. Because in addition, in radiative transfer theory, there are two definitions of fluxes. There is physical flux and astrophysical flux, and they differ by pi or 4 pi or something like that. It's really a catastrophe. Anyway, just a flavor, let's say, of this radiative transfer concept. This is very, very classical concept in the sense that you don't imagine single photons traveling, but you consider light rays, like classical thing. So you have a source of radiation, and then you have you put here a plane. It does not have to be perpendicular. It can be inclined, whatever. And then you are still interested in photons which are in the flux, which is going in this direction. So of course, this source is radiating in all those directions. So the basic concept is the intensity. This is not simple to understand. The formal definition is like that intensity is the proportionality coefficient in this equation, which determines the amount of energy which is going through the surface A, inclined under cosine theta with respect to the line joining, and it is measured per unit mass, per steradian, per unit frequency. So this concept is developed in order to disentangle two things: geometry and absorption or scattering. So this quantity, when measured from some distance from the source, for example, here, 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 this quantity does not depend on the distance if there is no absorption or scattering. It's not intuitive. I don't know how to explain it better, but on the other hand, so, and this quantity depends on two vectors, right? One is this r vector, the other vector is n. So, on the other hand, what you physically normally measure is the flux. And the flux, you get the flux by integrating viscosity over the angles to get the steradian here, get out from this steradian. And the flux from the source indeed depends on the distance, which you can somehow symbolically show that if you have a source here, you first measure flux here, and then steradian is large. Now you measure it here, and then this angle becomes much smaller. And in this way, you see that the measured flux drops with the radius as r squared. But the intensity does not drop. So this is a kind of approximate expression showing you that flux depends. On the other hand, the intensity does not depend. And all geometry somehow is encoded when you calculate flux from the intensity. And the radiative transfer itself concentrates just on the on what is happening to this intensity. And normally, if you have no emission from the medium coming, no absorption, extinction, scattering, whatever, then intensity is constant, as I told you. On the other hand, the basic equation of the radiative transfer is that if you measure how the intensity changes along path S, it is decreasing if you have certain scattering or absorption. On the other hand, it may also increase if you have additional remission from the matter, which appears all of a sudden. And of course, if you have also scattering, then you can have a line of sight, which is different, and then you scatter photon, and then this photon appears along your line of sight. So this is the source function, so-called. And this part looks like it's only decreasing the intensity. On the other hand, it also it contains stimulated emission. So if you have laser action, actually this coefficient can be negative. So the weakening is negative, which means you enhance the radiation. But apart from laser action, laser whatever, then normally this is the part which decreases the intensity. This is the part which increases the intensity. And in general, solving this equation is very complicated because you need to know everything about the material. But sometimes you can simplify things, although for a moment, it's not always. So special case is black body emission. So then the intensity is just the Planck function for a given temperature. More general case is a thermal emission. Thermal emission means that the matter is in balance with radiation. The temperature of the matter is the same as the temperature of radiation. So then this intensity here can be replaced by B, but you still can have source function in that case. And because in this case, the intensity, if this radiation is uniform, isotropic, then finally there should be no flux and no change of intensity. And in that case, you have a balance between the absorption and the emission. And this is so-called this Kirchhoff law. Of course, in the general case, there are difficulties, and I should mention already this problem that this form does not include Comptonization of photons, which changes the frequency. Here, those processes preserve the frequency. So you must know a lot to solve any equation. But we are now interested in optically thick case. That also is a chance to simplify the situation. And as quite frequently in radiative transfer, you have to play some kind of a game. You look for a formal solution, and then formal solution or rearrangement of terms allows you to get something. So this is formally a general statement, right? On the other hand, now what we do is we calculate I from this equation, just rearranging those terms. So now this goes to that. We have to divide by alpha. So this is divided by alpha, by the opacity. And we still have this term. Now we say that we are basically interested in z direction, but of course, in general, the equation radiative transfer should be solved in any direction. So along this S direction, we introduce here I, and cosine I we mark as mu. So now we look at the structure of this term. This is isotropic term, and this is not isotropic term. So in the optically thick medium, isotropic term does not contribute. Because now we will try to calculate the flux, integrating with respect to all angles. So isotropic flux will give nothing because the same amount of photons is going in this direction and in this direction. But here we have a derivative, and here we have additional mu here. So here we will integrate mu square. So this isotropic term will give us nothing, but this anisotropic term, which shows that intensity is a function of the disk thickness, this will really contribute to the flux, because the flux will be given by the difference. So formally, you have to integrate this over those angles, and this will give you positive thing. Now we have to assume that this radiation locally is a black body. We anyway assumed that the black body emission comes from the surface, so it's not surprising that we assume that inside the disk we also have more or less black body emission. But then we have here this derivative with respect to z. So this is the derivative of the Planck function with respect to z. And we can express this as a derivative of the Planck function over time, over temperature, times derivative of the temperature with respect to z. Because the Planck function depends only on the temperature. So this is like changing of variables. So now we can easily also integrate this mu squared. All those terms do not depend on angle, because B Planck function does not depend on angle. And derivative, this also goes out. And we will end up with such equation, which is kind of promising because it has the derivative of the temperature with respect to z. This is what we wanted. It almost looks like an expression for the vertical gradient of the temperature. And here we have flux. Only this part looks not yet usable, right? Quite complicated. But fortunately, we can introduce something which is known under the name of the Rosalind mean. And this is the Rosalind mean opacity. The structure of this expression is awful, but this is really designed to get rid of the frequency dependence of the opacity. So this is frequency integrated opacity, but integrated in a very special way. And using this, you can get a very nice and simple expression. And this we will use for the disk vertical structure. And to get that from that with that will be the homework for you. Pretty complicated. But it will let you see why the definition is like this. this opacity which is now here does not depend on the frequency, and it contains electron scattering and absorption part. And sometimes analytical expressions are used, or limits, and we will go to this issue again. But if you want to solve vertical structure properly, it is much safer to use tables. There are public tables, many tables of this opacity as a function of density and temperature. This Rosalind mean. So this equation is what we needed, only it is written in not a classical form. So we will soon rewrite that. So briefly mentioning special cases, if you have only electron scattering, then the value in CGS, it is in centimeters per gram, is 0.2 times 1 plus x. So this is x is the fraction of hydrogen atoms. And actually this is directly related to the Thomson cross section. It's more or less Thomson cross section divided by the proton mass. Right? This coefficient is just more fancy depending on the ionization state of the matter. If you are desperate, and we will be at the end of the lecture, for the free transition, you can use this kind of approximation with the density, linear dependence on density and very strong dependence on the temperature, T2 minus 3.5. So it's a strong function of the temperature. So this Rosalind mean is not the only mean which is used in stellar atmospheres or in a stellar structure, because it's not just for accretion disks, for star structures as well. This was the Rosalind mean which we will be using, but there is also another quantity which is also frequency averaged opacity, and this is the Planck mean, not Rosalind mean. We'll use this one. This one is used to describe the atmosphere, but in accretion disk we never bothered to switch between one and the other because it's too complicated. So we always keep that one. So this is useful to calculate the radiation pressure close to the disk atmosphere.
How do people get to these expressions, the opacities?
Well, this looks kind of direct, right? Because if you have an emission from the disk surface, then B looks like a flux. So you integrate opacity times, and then that expression looks like a force.
I'm talking about the free one.
Ah, this. You have first to determine the formula for Bremsstrahlung. And there you notice that the dependence is as t to half, square root of t. And then you use a Kirchhoff law. And B is t squared, t to the power 4. And then t to the power 4 minus half from Bremsstrahlung gives you 3.5. So you actively calculate Bremsstrahlung, and then you get that from the Kirchhoff law.
Thanks.
Mm-hmm. So as I said, this form is not nice. We like differential equations with derivative on the left-hand side and expression on the right-hand side. But so this is the elegant form. So summarizing, if you really want to calculate the disk vertical structure, so at a given radius, all functions depending on z coordinate, you have to solve those three equations. You have to use, of course, the prescription for the pressure, because otherwise you would miss one expression. You need the density, you need the opacity, you need this Rosalind mean from the tables or whatever. And you can worry what happens to the equations which we had previously, like those vertical, those expressions for flux. Yes, this is still needed because those are key parameters, accretion rate and black hole mass. But this is not a differential equation. So this enters the problem as a boundary condition. As a boundary condition for those equations, because here those are differential equations, they need boundary conditions. So as I mentioned, on the disk surface, you know that the density is equal 0, but on the other hand, you don't know a priori this disk surface height. On the other hand, you know some boundary conditions in the equatorial plane, because the flux should be equal 0 in the equatorial plane because of the symmetry, right? Because above the equatorial plane, flux goes in this direction. Below equatorial plane, it goes in this direction. So to match those two smoothly, you have flux 0, and then by integration, you build the flux to match this value at the surface. So the situation is not simple. You have some boundary conditions in the equatorial plane and some boundary conditions at the disk height, thickness, which you don't know a priori. So then you have to solve those equations either using relaxation methods, or as I do normally, you do this iteratively. So in my program, for example, Sagata, we have this program since many years. We assume the disk thickness, whatever it is, and then we know the temperature, the effective temperature. We know the flux, density 0, and we integrate this down. But if our guess about the disk height is wrong, then after integrating this equation, we will not get 0 in the equatorial plane. Either our flux will finish before, or we are getting to the equatorial plane and still some flux is left. So wrong. You have to change the height. And after adjusting this height several times, of course, by the computer, you can get finally the solution satisfying both boundary conditions. So it's an iterative process. In relaxation method, probably this is simpler, but there is one more thing here which I did not decide to elaborate a lot, because then we would have to talk even more about the radiative transfer, and we would have to talk more about Eddington approximation. The point is that if you really consider this upper height of the atmosphere, you notice that the temperature at the upper part of the atmosphere is not equal to the effective temperature. It can be intuitively understood in such a way that actually you see photons mostly from the depth of the atmosphere, where half of the photons get out without any interaction, absorption or scattering. So the effective atmosphere is defined a bit deeper than at tau equals 0. And it's quite complicated to show that this tau is actually 2/3, not half, as you might think intuitively. So at this tau equal 2/3, at this tau equal 2/3, half of the photons will come out without interaction, and half will interact and get back and down, and they will not be seen. And doing this Eddington approximation, you can actually show that this relation is correct, that T24 at the disk surface is equal half of the effective T24. So it's not a huge difference, because actually in the temperature it is a square root of 0.5. So it's 0.8. If you calculate square root of 0.5, it would be 0.7, 0.85, right? But if you want to do things properly, then this is one more correction which you should do. And there is one more thing which I will also not discuss. In the case of accretion disks, like in the case of stars, convection can develop. And I don't know if you are familiar with the interior of the stars, but convective motion can actually be responsible for most of the energy transfer from the deep zones to the upper part. For example, this is the case of the sun. Parts of the sun are dominated by convection, and actually most of the energy comes out with a kind of convection. Normally those who do cooking from time to time, of course, are familiar with convection, right? Because this is how the cooking proceeds. You heat from the bottom, and then your soup is boiling. So it's not radiative transfer, it's purely convective transfer. 99%, I guess. This is why if you have thick soup, it's quite possible that it will stick, because this convection will not work efficiently, and you will burn the bottom while keeping the upper part of the soup still unheated. So in principle, this equation can additionally include the option of convective transfer. But then you have to check whether your disk is convective or not convective. You can have convective zone, radiative zone, convective zone, whatever. That becomes much more complicated. But of course, computer programs can do that. And for example, the code which was published by Agata Różańska, she's the first author of this in '99. It solved everything. It even has a corona on the top of it. So this can be done. So sometimes we really want to solve all this vertical structure. And this is important when we want to know more about time scales, sometimes about time behavior. If, for example, the disk is irradiated from the outside, then also this irradiation, this additional radiation will interact with the material, and then the upper part, the structure, are important. On the other hand, in many situations, vertically averaged or integrated things are just good enough. And in that case, as I told you, if you don't worry about coefficients like factor 2, 3, whatever, you can change this hydrostatic equilibrium equation in this way that it's 1 over rho p over h, and here z replaced with h, and then you drop, of course, the sign because then it does not have any meaning. The same for this equation. Here you have f rad divided by h, and then this pressure should be understood as the mean or equatorial value, whatever. The same is for this equation. So you have T over H, still this Rosalind mean and flux, and T cube. So from this last expression, you can already see, you can already have some insight into the equatorial temperature of the disk. Because, you know, here is T cube, here is T, so you can combine that to get T to 4. And then remember that effective temperature is also T to 4, right? Flux is sigma times effective temperature. But in that case, we still have here H and opacity. And H times opacity, this is the total optical depth of the disk. So of course, coefficients are not correct because I dropped this 3 over 16, whatever, because I told you coefficients are not here important. This is just hand waving. But you can see that this is the difference between the equatorial temperature. You have here the total disk thickness and the effective temperature where you don't have this expression. So the total optical depth of the disk is usually of order of 10 to 4, roughly. That means that the equatorial temperature is more or less 10 times higher than the effective temperature. More or less. Of course, it depends on the disk part. But more or less, it's factor 10. So it's not like in the sun, for example, where effective temperature of the sun, what is the effective temperature of the sun? 4,000, 5,000?
Around 6,000.
Yeah.
That's the surface temperature.
Yeah.
Surface.
Surface or equatorial, whatever. I mean, effective temperature. But the interior is a kind of million, right?
Yes.
So this ratio is really huge. It's orders of magnitude, 3 orders of magnitude. In the case of disk, it's just 1 order of magnitude. But still, they are not quite isothermal. So this is something which already comes out from this vertically average thing. Simple estimate. And actually what is discussed mostly in Shakura-Sunyaev paper, but not only, they have full vertical structure, equations of the vertical structure, but what people use this paper, Shakura-Sunyaev 73, most of the time, is for solutions which were obtained using this kind of approximation. So average or vertically, whatever. As I said, coefficients are not so important. The second part is that if you want to provide people with analytical solutions, you have to simplify something, or at least you have to divide the solution into zones. Because you know, if you have equations like this is not a problem. This is just a boundary condition which will appear in all those things. here you have a chance to get power law dependencies, but you cannot get a power law if you have plus here, or if you have plus here. Those are, sorry for that, those are troublemakers. So you have to make a decision whether this dominates, radiation pressure dominates inside the disk, or gas pressure dominates inside the disk. And this, the same about opacity. You have to make a decision. Do you assume electron scattering, or do you assume this absorption? If you assume this absorption, then you can use this free, which I showed you, and then you have complex dependence on density and temperature, but still it gives you a chance of getting a power law solution. So this is what Shakura and Sunyaev in this classical paper did. They proposed 3 solutions for 3 regions. They are more careful. They call those regions A, B, and C. But I use the colloquial expression, which is most frequently used: inner, middle, and outer. And there will be a warning soon that this is really dangerous to take it literally. But anyway, so notation A, B, C is better. And you will see in a moment why. So indeed, in the inner region, they assume that radiation pressure dominates and electron scattering dominates. In the middle region, still electron scattering dominates, but the gas dominates. And in the outer region or C region, everything is cooler, so you don't have that much radiation pressure, you have gas pressure, but also you have free opacity because material is not so highly ionized that electron scattering does not dominate. So it is intuitively correct. On the other hand, if you calculate things really numerically without dividing disk into zone, you have a problem with this middle zone. It's almost never applies in practice. Because at least in many cases may depend on the mass. When you start to be dominated by gas, also this starts to be important. But certainly inner radiation pressure dominated region, domination by electron scattering, this is a very nice solution, and the outer region is a very nice solution. So I didn't copy everything from their paper. I also did not rewrite their notation because this is always immediate source of errors. But I copied some equations to comment on them. So they express everything in dimensionless units. This small dot n, this is more or less Eddington ratio within a factor 2 or whatever. You can check that, but it's basically Eddington ratio. A black hole mass is expressed in solar masses. Here you have to be careful. For the unit of radius, they used 3 Schwarzschild radii. So RG for them is Schwarzschild. I told you it's better not to confuse those things, but you know, in the old times, nobody thought about using full GR to solve those problems. But anyway, it's explicitly written here. But yes, I wanted to start with the inner region, not with the middle region. Sorry. So in the case of inner region, we assume that disk is hot, so radiation temperature is high, T24 is high, radiation pressure dominates, electron scattering dominates. And for that, they determine the solution for the disk thickness in such form. This is their misprint, of course, it's R here. But it was copied from the original paper. So you see there are misprints in original paper as well. You should always think what you are doing. Anyway, this is this boundary condition. But otherwise, you see there is no dependence on the radius in the prescription for the disk thickness. So the disk thickness, when the disk is dominated by radiation pressure and electron scattering, the disk thickness is constant with radius. The disk is flat. This is really very important statement. And of course, it's zero when you are at ISCO. What in addition you see is that this is proportional to the Eddington ratio. So for example, if you express this disk thickness as a function of Schwarzschild radius, the Schwarzschild radius will also be proportional to the mass. So the mass will vanish. But this dependence on Eddington ratio will remain. And this is exactly why if you go high with Eddington ratio, forget about using standard accretion disk, because this thickness divided by the radius, at least in the inner part, will be comparable to 1. So then you have to use different equations. You have to go to slim disks. Then the second interesting equation is the surface density. Surface density is the density times the disk thickness. So it's also proportional to the optical depth. So if you use this, so this surface density has the following properties. It rises with radius. Okay, why not? But it decreases with the accretion, with the Eddington ratio. And that will be a source of problems. That will be a source, exactly a source of problems with disk stability. And we will talk about it not on the next lecture, but the lecture after that. So our fantastic accretion disks are actually unstable. And this is the place where we already see that, but we will talk about it in detail. And then pay attention to this problem. If you put here the value of ISCO, this is 1 minus 1. This was not a problem here. 1 minus 1 is 0, and you are not surprised to have the disk thickness 0 at ISCO. That's fine. But here you have 1 over that stupid thing. Your surface density goes to infinity. And many people sometimes were quite confused by this fact that they use prescription for the innermost part. They get infinite density, infinite opacity at ISCO, and it's like a catastrophe. And then it might suggest that you immediately have to change equations. This is not true, and you will see that in a moment. But let's go through other regions first. So middle region, it's weakly really depending on viscosity. I mean the disk thickness, slightly depending on accretion rate, but rising almost linearly now, rising with radius, right? So the disk starts as flat and then it starts flaring. And the surface density now rises with accretion rate. And that will suggest later that this part of the disk is stable. We'll talk about it. So the disk rises. This is the important part for the middle region. But I told you the middle region is realistically not very profound and not a good description. But outer region is a good description of the outer part of the disk. And when you look at Shakura-Sunyaev prescription for the disk thickness in the outer part where you have gas domination and free domination, again, the radius, the disk thickness rises almost linearly with the radius. So you continue really with this disk flaring. So sometimes people people draw that this inner disk is like this, and then it's something like that. No, it's flat and rising. That's the shape of the disk. Not like bump. It's nothing like that. And the surface density somewhat drops with radius, so sometimes you can have a problem there, but well, it rises with accretion rate, so then this solution is stable. And this is what you actually should do if you want to use Shakura-Sunyaev prescription. So I told you this statement that inner region is sort of misleading. Of course, most of the inner part, when you have reasonably high Eddington ratio, is described by this expression. But actually, when you start from ISCO, you should first use outer region, then middle region, inner region, middle region, outer region. And then you can have a solution which is reasonable all the way practically down to ISCO. This is not a problem, because if you look at the outer region solution, so now I will try to go back. This surface density goes to 0. So it does not go to infinity. You don't have infinite mass. Of course, you have slight problem with velocity, because then if this surface density goes to 0, then for a fixed accretion rate, your radial velocity goes to infinity. But who needs radial velocity for calculating spectra or whatever? So this is not really dangerous. If you don't touch radial velocity, this approach is correct and gives you always reasonable results. This transition happens really very close to ISCO. So it's almost I think if you start at 3.5, you are already here. But in this way, you avoid having infinite problems with surface density, amount of matter, whatever. So now we can also use those expressions to see when this inner region is actually dominating. So we assume that we are.
So this is the actual structure of the disk, like outer, middle, inner, middle, then outer.
Sorry.
So this is, I mean.
Yes, this is how you should use. So actually, in every region, you should check which part you should use, right? Of course, if you do it numerically, using numerical code, which does not require regions, then it's not a problem.
Yes,
right?
Each radius.
But actually, close to ISCO, you can notice that flux is low. Temperature goes to 0. So then free dominates. It's just a matter of checking which region you should use. Because you have very low temperature close to ISCO, because you have no dissipation close to ISCO. And that's it. But of course, because the maximum temperature is quite soon after ISCO, right? At 4, then you pass through those regions really rapidly. But formally, that's it. So assuming that we are interested in this inner region, we can calculate using the previous expressions the ratio of the radiation to the gas pressure. I dropped coefficients, so probably I should rather write proportionality. But what you see here is that the ratio is proportional to the Eddington ratio square times the mass to the power 0.25. So that means, of course, that if you have a high Eddington ratio source, then your radiation pressure is important, and then this region will be extended. But that term is also important, because if you think about galactic sources, you really need high Eddington ratio to have this inner region. In many sources, you don't have it at all. On the other hand, if here you have a black hole mass 10 to 8, that gives you a factor 100. So in AGNs, practically all accretion disks have this large inner region, unless you go to very low Eddington ratios. So this is a systematic difference between AGNs and galactic sources. It's important to remember later also in the context of radiation pressure instability. Okay, and then I wanted to mention the paper which was the topic of my PhD thesis. Then I had a different name, very difficult to pronounce for foreigners. That was Muchotrzeb. Difficult even for Polish people. So when I got married, I changed the name and I didn't return to this one, never ever. I mentioned to you that if you really use this Newtonian approach, you have radial velocity infinite at ISCO. And if you want to do better, you have to do better. So you have to go back to the equation which I already showed you. That you cannot, in that case, use the Keplerian disk everywhere. You have to keep the radial pressure term, and you have to keep this velocity, radial velocity term. And to be consequent, you also have to keep additional term here. This is the advection term. So here is this, let's say, heating, here is cooling. This is the radial flux, radial radiation flux. This is not really important, but for generality we kept that. But this is the amount of material which is flowing with the stream, and it's not locally re-emitted. So close to ISCO, actually this term tells you that there is no dissipation and you have a balance between this term and that term. And close to ISCO, all those terms are important. And if you rewrite this equation using continuity equation, it's not needed to solve the equation, but you see that the following structure, that the derivative of the radial velocity over radius is equal something, something pretty boring, and then radial velocity times 1 minus, and this is the sound speed divided by radial velocity squared. This is exactly like in the case of Bondi flow. So you have transonic solution, really very close to ISCO, and then supersonic flow. So I told you that in the Keplerian disk outside, you have highly subsonic radial velocity and highly supersonic velocity in fine direction, while below ISCO, you will have highly supersonic velocity in the radial direction. So I wanted to show you a few plots from that paper. You see the difference between the publishing quality in 82 and publishing quality nowadays. At that time, it was...
What software was used to plot this?
I think it was done by hand.
Awesome.
If I remember correctly, yes. Because actually you see that, right? If you follow very closely, because I'm not sure if those kind of wiggling is really real. I wouldn't bet much. So I think I had numbers and then I had to plot that myself. So what is shown here is the disk thickness as a function of radius. And as I told you, ISCO is here at 3. So now we have, with Bogdan Paczynski, we determined the solution for 2 values of the accretion rate. That was 0.1 and that was 1 Eddington ratio. So we have the solution in all the region. Of course, we don't go to the horizon because that was done in pseudo-Newtonian potential. So we cannot really go even too close. That would be dangerous. But pseudo-Newtonian potential was quite good for that. Here is the ratio of the radial velocity to the sound speed, and this point marks the transition from the subsonic to supersonic flow. And you see that for the low accretion rates, this transition happens very close to ISCO. If your accretion rate is larger, then your transition moves inward. But that also depends on viscosity. That critically depends on viscosity. If you have large viscosity, it can be the other way around. And for large viscosity, you can have a transition to supersonic flow even before you reach ISCO. And then you have a lot of problems with unique solutions, etc., etc. Anyway, a comment on the magnetic, on the shape of the angular momentum. So here you see clearly what happens to the angular momentum. So this is the Keplerian angular momentum in pseudo-Newtonian potential. As I told you, this minimum is at ISCO. And this is the actual solution. So for low accretion rate, it almost follows the Keplerian thing, and then it becomes shallow. So the rest of the accretion proceeds with the constant, almost constant angular momentum. And for high accretion rate, the departure is more noticeable. So if you want to describe this region below the ISCO, close to ISCO, you should include those terms. If you want to calculate the spectrum of the Keplerian disk, and the disk satisfies the assumption that this thickness is lower than radius. You don't need this part because this is not really very visible in the spectrum. You have no dissipation here, right? Nothing happens. So it was just to know what happens physically, but it's not visible in the spectrum. On the other hand, if you increase the Eddington ratio, and if you go to slim disks, those are actually equations behind slim disks. Those are those equations, and actually the program is also the same, without any modification whatsoever. So as I told you, most of this lecture now might seem useless, because if you are quite sure that your spectrum looks like a Keplerian disk, you can follow the previous lecture, calculate the spectrum, and don't worry about the vertical structure. Forget it. On the other hand, if you have a situation which is time dependent, all this will be important. And then we will talk about that. But first, on the next lecture, we will have to talk about Comptonization. And then we will talk about time-dependent accretion disks. Okay, so that was homework, right? Yes, I mentioned that this is the exercise, just one this time. How you go from that equation to that equation, right? Using the definition of the Rosalind mean. Looks not simple, right? It requires noticing one thing. So I hope somebody will notice. Anyway, that's the end of the lecture.